invariance of virtual links and one object that allows to formulate or reformulate this invariance. So we will deal with virtual links that is that can be described by virtual diagrams. So that is for valent graphs with two types of crossings, classical crossings and virtual crossings. You can see an example here. And there are some transformation of this diagram called Radimasty moves for virtual diagrams. So there are two kinds of moves, the classical Radimasty moves and virtual moves, which include virtual crossing. So we have virtual analogs of classical moves and one semi-virtual move, which includes two virtual and one classical crossing. And diagrams model of these moves are virtual links. There is another way to describe virtual links, or more precisely virtual node, and this is Gauss diagrams. We can consider a virtual diagram with one component, and then take a couple and go along the virtual diagram and mark the moments when we pass through a crossing and through the crossing we pass two times, and if we move along the circle parallel to the move on the diagram, we will have two moments when that corresponds to one crossing. We connect this points with the and thus we get a chord diagram. And there are additional structures on this diagram. First, we have an orientation of the chords. The chords are oriented from overcrossing to undercrossing. And there are signs of the chords which corresponds to the signs of the crossing. So we have positive and negative crossings. So any virtual diagram can be described by Gauss diagram, and Radimasty moves of virtual diagrams correspond to some moves on the Gauss diagram. And we can define virtual nodes as Gauss, as equivalence classes of Gauss diagrams modular Radimasty moves on Gauss diagrams. If we talk about invariance of virtual links and nodes, there are different invariants and different constructions of such invariants. And since virtual links can be described, virtual nodes can be described by Gauss diagrams, and Gauss diagrams have no virtual crossings, for any invariant of virtual nodes or links, there is a definition of such invariant which doesn't mention virtual crossing. But if you look at known invariants of virtual links, you can see that some of invariants ignore virtual crossings. When you define invariant, you don't consider virtual crossing at all. For example, John's polynomial, if you define it through Kaufman bracket, you consider smoothing and don't pay attention at virtual crossing at all. And there are some other invariants which ignore virtual crossings, but there are a few invariants that use virtual crossings in their construction. For example, you can take some definition of virtual Alexander polynomial or virtual quantum. The definition of these invariants include virtual crossings in their construction. So one of my goal was to extract the information about virtual crossings and show how this information can be used to reformulate these invariants that based on virtual crossings without virtual crossings. So let us pass to the main definition, but before I say a few words about how virtual diagram and Gauss diagram are connected geometrically. Virtual diagram can be considered as immersion of four-valent graph into the plane. So we can consider four-valent graph G tilde in three-dimensional space and projection of it into the plane, and virtual crossing are just the place where two different arcs in the projection. And this intermediate current graph can be obtained from the Gauss diagram if you contract the chords of the Gauss diagram. So you have such a picture. There is a map from Gauss diagram to a four-valent graph, and then you immerse this graph into the plane and get a virtual diagram. And the edges of this intermediate current graph corresponds to long arcs of the virtual diagram, that is arcs of the diagram that starts at classical crossing and ends at another classical crossing. So we will deal with some cochain on these long arcs. So the main definition, the virtual index cost cycle. You take the current graph, or you consider the virtual diagram and long arcs of this diagram, and mark each long arc with the sum of signs of virtual crossing on this long arc. So if a long arc moves from left to right, if another arc intersects our long arc from below to up, we take the sign plus, and in the other situation we count this virtual crossing with the sign minus. So the sum of these signs is some integer value of a long arc, and thus we have one cochain of the current graph, or some one cochain on the long arcs of the virtual diagram. And we can consider this as one cochain on the Gauss diagram. We have some marks on the arcs segments of the core circle, and the chords in Gauss diagram have values 0. So this is our main object, virtual index cost cycle. Any questions? Is it clear how this was defined?
So could you trace your virtual trefoil and show us where you're getting the signs from? I think I missed that.
Okay, let us take this example, the virtual trefoil. So we have 4 arcs
Yes.
between these two classical crossings. The upper arc and this arc have no virtual crossings on them, so they have the the marks 0. And take, for example, this arc that starts here and move here.
Yeah.
And we have only one virtual component, and this virtual crossing is the crossing of this type.
Right,
This
right.
type.
Okay.
So we have the sign -1. And on the
okay, that's what I needed. Thank you.
Sign +1. So that's how these these numbers can be calculated. So so we have such a cycle, a chain called virtual index cycle. What are the properties of this chain? If you
sorry to interrupt, but it's a co-cycle. So what is the co-boundary of this chain?
Boundary.
The co-boundary.
We consider a graph of one-dimensional objects. So in fact, the boundary of this chain is 0.
Okay.
But if you look at for example, this proposition, the last property is that the sum of all numbers of all arcs are 0. I return for a moment on the previous slide. If you sum up all the numbers, you get 0. So if you consider the phone complex when you attach a disk along this node, so this two-dimensional cell complex have two-dimensional chain, and in this complex, this virtual index will be 0 due to this property. So this is one interpretation why it is called cocycle. So this cocycle doesn't change if you apply pure virtual randomized move, and if you apply semi-virtual move, the cocycle is changed by a co-boundary of the vertex which of the classical vertex which takes part in the move. So I switch to this. We have this randomized move. That means an arc with the virtual crossings pass through a classical crossing, and if you count the virtual crossings with signs, you see that this cochain is changed by this compoundary some compoundary term. So this property means that the homology class of this virtual index cycle doesn't change under virtual randomized move, and we can call this cohomology class virtual index class. So we have one-dimensional cohomology, an element, a distinguished element in one-dimensional cohomology. And in fact, if we take any representative, if we take one-dimensional chains, take any representative of this cohomology class, we can construct a virtual diagram whose virtual cocycle exactly this represented. So any representative is realizable as a virtual index. And the picture below shows how it can be done. You can take a simple transformation using virtual ready master moves and change your virtual cycle by a boundary. So if you apply this transformation several times, you can get any homologous cycle. And as for classical ready master move, we have two diagrams, D1 and D2, and they differ by ready master move. And we can also construct some intermediate diagram which corresponds to the single moment of the move, the ready master move. And the connection between index cycles on these diagrams can be described by the proposition that is there is a unique one-dimensional on the intermediate diagram which induces this virtual index cycle on D1 and D2. So this is because the small arcs that appear in the ready master move have no virtual crossings and they have max 0. So we can contract them without any hesitation. Let us construct another cochain that doesn't use virtual crossings but use only classical crossing. It is called canonical index. For any classical crossing, we take, for example, a left cochain. So we add -1 to the incoming arc from the left and +1 to the outcoming arc to the right, and the other two arcs have zeros. And if we sum up these cochains, we get some one-dimensional cochain on the diagram on the long arcs of the diagram. So in fact, if you sum up only left cochains or only right cochains, you get the same cochain as shown below. And in fact, on each long arc, the max will be either -1 or 1 or zeros. So both methods, left cochains beta L and right cochains beta R give the same result. So we have some one-dimensional cochain on the long arcs of the virtual diagram. And in fact, this is representative of the virtual index cycle. The homology class of this canonical index cochain constructed from the classical crossings is exactly the virtual index class. And this proposition means that there is some virtual diagram whose virtual index cycle coincides with the canonical cycle. And the picture shows what is this diagram. So you start with some virtual diagram and then construct virtual double. So you take on each component some point, for example here, and then apply the two move. You take small arcs at some point and replace this arc with a virtual arc with only virtual crossings that goes on the left to the to the component and in the opposite direction. So you take this circle and construct something that goes in the opposite direction, and for this to flow, you can do the same thing. So you get some diagram, and if you look at it, there are some any virtual crossing corresponds to 4 virtual crossings in this new diagram. If you look at it, these 4 crossings give zeros, number 0 on the intersecting axis, because these 2 parallel sides are directed in opposite direction, and the virtual crossings annihilate. And as for classical crossing, you have here 3 virtual crossing and 1 classical crossing, and if you count the virtual crossing with signs, you get exactly the cochain, the left cochain, beta L here. So this is the diagram that gives you a canonical index cocycle as the virtual index. And the theorem means that you can define that in fact, if you only count virtual intersection with signs, you can rely only on classical crossings. So you can get such special diagram, and you can only pay attention to classical crossings. And this theorem allows to reformulate some invariants that use virtual crossings in a way that relies only classical crossing. Okay. And this picture shows why the 1 cochain I introduced was called index cocycle. If you take a crossing, if you take a node and a crossing C in the node, you can consider oriented smoothing at these crossings, which splits the node into 2 halves, right and left. And if you take left or right half, depending on the sign of the crossing, so we can define positive half and negative half. The value of this half, of the positive half, of our virtual index cocycle is called the virtual index of the crossing. The virtual index of the crossing. So this is a definition of the virtual index. And the next slide shows that virtual index coincides with the usual index. So what is the usual index? You take the positive half of the crossing and counts the number of intersecting of the number of classical crossings on this half counted with the sign. The signs are shown in here, so you can see that the signs are opposite to the signs of the definition of virtual index cocycle. That means if the intersecting arc goes up, then we assign the mean minus the negative sign, and if the intersecting arc goes down, we assign a positive +1. So the sum of the signs on this positive half d plus c is is the index of the crossing. The index is a characteristic integer number of the crossing, which was used to construct many polynomial invariants of virtual nodes. And this is the definition. And you see, if you take the canonical index K-cycle, you see that this value of canonical index K-cycle on the positive half is coincides with the index. And that means that the virtual index and the classical index is the same number. That's why this K-chain was called the index K-cycle. Okay. Let us present another representative of the virtual index class. Let us consider these virtual K-chains on the Gauss diagram. So we have virtual diagrams, and we can assign, we can consider the corresponding K-cycles on the Gauss diagram. That is, we have some marks on the boundary circle, and the codes are marked with zeros. But we can there is a unique homologous one K-chain that has zeros on the boundary circle, on the code circle of the Gauss diagram. We can by adding co-boundaries change this K-chain with the K-chain that have zeros on the boundary diagram, and this K-chain is unique, and the numbers we get on the codes are exactly the indices of these codes. So you can construct the index, the homology class of this virtual index K-cycle on the Gauss diagram, just as you should assign to each chord its index and take zeros on the core circle. Okay. So another property of a virtual index K-cycle is the following. Let us consider an oriented link. Then you can take any component of this link and calculate the values of virtual index K-cycle on this component. And these values coincide with the regular number. Up to sign these values coincide with the regular number. The regular number is the difference between two linking coefficients. You can consider overly linking coefficient, linking number, where the components goes over the other component, or linking number when where the component, the distinguished component goes under other components. So there are two numbers. They are invariants of virtual links. The difference between them is called regular number, and up to sign, this is exactly the value of virtual index K-cycle on this component. And here we have an example of this this regular number. We have a two-component link. Here there are one crossing and there are two long arcs. If we calculate the virtual index K-cycle, this arc has the number -1 at this the number 1. So the value of d1 is equal. The value of d1 is -1, and it differs by sign from the real number. The real number, and this exactly, and this holds also for the and so the next property of a virtual index cycle is the following. Given a virtual diagram, we can construct a two-dimensional oriented closed-oriented surface by this diagram. Let us consider crossings. For classic crossing, we assign stuff this part a cross, and for virtual crossings, we have two non-intersecting ribbons, and then you glue together these surfaces with boundary, and you get some oriented surface with boundary. Then you should glue or the boundary with the disks, and you get closed oriented two-dimensional surface, which is called Venn diagram. And the node, the virtual node or link, will be one skeleton of this surface. So you can consider this virtual index cycle as an element of one-dimensional cohomology of this two-dimensional surface. And this will be a cocycle. That means if you consider the differential of this cycle in this two-dimensional cell complex, you get 0. In other words, for any cell of this abstract line diagram, the value of the virtual index on the boundary of this cell is 0. So this is another reason to call this object VID a cocycle. Okay. And now let us pass to invariance. Let us consider a virtual index polynomial. It is an example of invariance that uses virtual crossings in the definition, in construction. This is an invariant defined in one of the articles in Kim and Park. They consider it oriented virtual link and distinguished self-crossings and mixed crossings. For self-crossings, they assigned to each self-crossing its virtual index. That is the sum of signs of virtual crossings counted on the positive half of the link at this crossing. And for mixed crossings, they consider it the virtual intersection index, which is coincide with the value of virtual index cocycle on one of the component of that intersects at this crossing C. So the definition of this virtual index polynomial can be written as a polynomial. They take signs of the crossing, multiply some formal variable, power this virtual intersection index, and these intersection indexes initially were calculated by using virtual crossings, but because of their values of the virtual index cocycle on some some half or components of the link, we can reformulate them in the following way. We replace for self-crossing this number with the index of the self-crossing, and for mixed crossings we take the regular number of these two components. So we get this formula for this polynomial invariant, and these numbers can be calculated using only classical crossing. So this is an example how we can formulate this invariant using only classical crossing. And another example is the virtual bike window. This is a generalization of bike window given by Kaufman and Mankarov. I recall that bike window is some set with two binary operators on it. We have this property of the bike window. The result of these two operations coincides when we take x and x. These operators are invertible in some sense. These are properties of two, and the second and the third property. We have some invertibility property and some distributivity property. This three question. And virtual bike window is bike window with additional operator f, which should be an automorphism of the bike window. That means that we have these two equalities. And these properties and these properties of virtual bike windows come from current condition. If you have a virtual diagram, then you can color the short the arcs of the diagrams with the elements of the bike window, and the coloring is good if you have the following compatibility condition at each crossing. When you deal with a bike window, you don't pay attention to virtual crossing and consider currents of long arcs of the diagram, and this this condition at classical crossing. When you consider currents by virtual bike window, you consider short arcs. That means short arcs is a part of diagram, an arc whose end can be virtual crossing or classical crossing. Each virtual crossing is the end of 4 short arcs. We should have the following condition at virtual crossing if you consider virtual bike window. So, if you take all the possible of all good currents of a diagram with the bike window or virtual bike window, you get some set. And for diagrams which differ by radius move, there is a one-to-one correspondence between these current sets. That means, for example, if you take a finite virtual bike window, the number of currents will be the same for two equivalent diagrams. That means the number of currents is an invariant. And the following theorem shows that if you consider covariance with the elements of a virtual bike window, you can replace this virtual bike window by some bike window. Bike window with these two operators, so you can check that these operations define structural bike window, and there is a bijection between currents of any diagram with a virtual bike window BF and this twisted bike window P of F. And the picture below shows how this equivalence can be. You should take some. You should take a left double, virtual double of the diagram, which gives you canonical index co-cycle as a virtual index co-cycle, and then then you assign to any covariance of the virtual bike window this covariance. That is, if you take covariance by a virtual bike window, you should assign some colors to the long arcs. You should create some loops with the virtual first ready master move, the colors on these loops, and this will be the colors by the twisted bike window. So we have this one-way bijection, and that means that invariance of the virtual bike windows are in fact invariance of bike windows, of twisted bike windows. And for example, if we consider Alexander virtual window or Alexander bike window, Alexander virtual Alexander window is a window with these operations, and this if we consider covariance by this virtual Alexander window, they are corresponds bijectively to the covariance by this twisted Alexander window, which is called Alexander bike window. And that means also that the model generated by the arcs of a diagram modular relations from these crossing relations gives you the same modulus, and the fitting ideal of this moduli, which are the virtual Alexander polynomial, will be the same. So this equivalence shows that we can define a virtual Alexander polynomial by a bike window with these operations, or we can use a virtual Alexander window with define virtual Alexander polynomial, and this will be the same polynomial. Okay. Next, let us consider index car cycle modulo 2. That is, let us count the intersection virtual crossings on each long arc modulo 2. And that means we can we don't have signs, or in any case, each virtual crossings add 1 to the value of a long arc, the diagram. We have the same theory of this factorization modulo 2, and we call this reduction of circle index of virtual index car cycles modulo 2 by parity car cycle. So we have all parity car cycles belong to the same cohomology class on this covering graph with coefficient in Z2. And we have also canonical parity car cycle, and the value of this parity car cycle on half of the crossing is the Gaussian parity. So that's why this car cycle can be called parity car cycle. And parity car cycle can be doesn't depend on the rotation of the diagram, but if you have a link with several components, the canonical this canonical cycle depends on the orientation. When you consider this, the number of the virtual crossing modulo 2 on the log arc, you have the form property. Let us consider smoothing of diagram. At each crossing, we have two types of smoothing. If we smooth each crossing somehow, we get what is called Kaufman state of the diagram. And if you take some component of this, will be a diagram without classical crossing. And that means it is several components with only a virtual crossing. And if you count virtual crossing on each component, the sum will be 0. So we have the form proposition that we consider a parity car cycle that its value on any component of any Kaufman state, this value will be 0. And when we deal with the with these parity car cycles, that means we can have only two values for each arc, 0 or 1, and we can draw this with the dots or cut lossy. For example, if we take this diagram and try to calculate the virtual parity, virtual parity car cycle, and we take any long arc from classical crossing and calculates the number of virtual crossing on it modulo 2. So we have two arcs with one crossing, one virtual crossing, and we mark this arc with dots. And we have two arcs, two other arcs with an even number of virtual crossing. So these arcs without. And we can place on any arc more than one dot, but in this case we have this contraction rule: two dots contracts. So this is a graphical way to write down the co-cycles with values in Z2. And there is a connection between these parity co-cycles with the what is called sourcing structures. Let us take a diagram and take a crossing of this diagram, and then we can introduce a sourcing structure at this crossing in two different ways. Sync structure means that if we have these crossings with the four vertex of with four incoming crossings, we choose two opposite edges and say these edges are incoming edges, and two other opposite edges are outcome. So we have a structure. So we can choose one of these two opposite edges as incoming and the other two outcome. So there are two possible sourcing structures at any crossing. If you have an orientation of the diagram, you can assign to new crossing this canonical sourcing structure. So the outcoming edge to the right remains outcoming edge. So and you choose this structure at any crossing of the diagram. Yes. So if you have n crossings, you have 2 power n choices. And so let us call any set of these choices local sourcing structure, and we have 2 power n these local structures. Let us denote the set of these structures by lambda g. So if you choose some local sourcing structures, then there are two types of edges. There are edges when where the orientation at the end of this edge disagree, and you you put a point on this edge. And for the edges where the orientation at the ends agree, you put nothing. That means that to any local sources structure, you can assign one cochain with the values in Z2. And the proposition is what you get is parity cochain. And in fact, you have a almost bijection between local sources structures and this set of parity cochains up to switch of orientation at each crossing. If you change orientation at all crossings, this cochain remains the same. So up to this global switching, you have a bijection. And one of the corollary of this property is that if you have if the class of this parity class is 0, then you have a diagram with zero virtual parity cochain, and you can establish a global sourcing structure on this diagram. That means if you construct an abstract link diagram for this, this diagram will have a checkerboard column. And we can use this correspondence between vertical cycles and local sourcing structure in the construction of Chavanov homology for virtual links. The definition of the general definition of Chavanov homology of virtual links is due to Vasily Mantorov, and 10 years later, his construction was reformulated using these dots. And now here I gave another reformulation, just reformulation of the construction. So, in order to construct Chavanov homology, Chavanov complex, and differential, you should take the following. Let us consider virtual link diagram, and then we can assign, can consider all smoothing of this diagram. This called Kaufman states. We need also some additional structures to construct the differential of the Chavanov complex. First, we need a local sourcing structure on the diagram. Then some oriented direction. We need it to cancel the complex. I will talk about it a bit later. Then, for each Kaufman state, which is a union of circles with virtual crossing, we should somehow order these components of the Kaufman space and choose a point on each component. These order and points on each component are part of the space. So, assume we have chosen the local sources structure. Then we have one cycle on the diagram, and that means we have something like this. After we smooth take smoothing of the crossing, we will have a diagram like this. A diagram where we have crossing and dots on the diagram. And then we consider enhanced Kaufman states. That is, we mark each component with 1 or x or minus x. So if we mark component with 1, we mark all arcs of this diagram with 1. But if we take x, we should change the sign of x when we pass through a dot. So here we have this enhanced Kaufman state. The mark here is x, and on this mark, between these two dots, we have the mark minus x. And here we have another example. So, and because we have an even number of points on each smooth component, this is correct. And we call these diagrams the enhanced Kaufman state, and they are the generators of the Chavanov complex. Generators of the Chavanov complex, and 1 and x are the basis of two-dimensional two-dimensional space we call V. So if we choose a Kaufman state that is some smoothing of the component, then we should order the component and take points. On each component, we take a point. If we take this additional structure, we can identify the enhanced Kaufman states with direct product, some basis of the direct product of this two-dimensional space V generated by 1 and X. And that means if we have some enhanced Kaufman state, that it's we mark these components somehow. We take the first component and take the value at this point. It will be 1 or X or minus X. Then we take the second component and the value at this point, and then we take the product of these marks and get an element on this space. For this choice of order and these points allows to identify the space of enhanced Kaufman states with this product. Okay, and then we should define the differential. The differential corresponds to switch between two smoothing. We take one crossing and change one type of smoothing with another, and we have three situations: splitting, merging, and single circle array when one component transforms into one component. To this situation, we assign 0 differential, and to this to transformation, we assign correspondingly either multiplication of this Frobenius algebra or co-multiplication. But before this multiplication, co-multiplication, we should assign some operator tau, which in the operator tau, yes, the operator tau change the sign of x and do nothing to 1. We apply this operator before and after. And this map applies the number we apply this map tau depends on the number of points between the crossing when we switch the smoothing and the distinguished point on the component. This picture shows if we have two points on one component, we consider the number of dots on the path from point P to point Q. And this number doesn't depend on the which side we move from P to Q. So we take the power with this. This will be 1 or 0. And the composition gives us such map. It is almost the differential, but we should define the sign of this differential. And here we need some additional structure called direction. Direction means that if we have a local sourcing structure, we take a square dot, on one of the incoming edges. if we choose one of the incoming edges, then we can number the adjacent regions by 1 and 2 as on the figure. So this dot means that the adjacent regions are 1 and the other 2 are 2. And using this, we can define a local order of the component that goes through the crossing. We have a picture, we have two types of movement, and we number, if we have number these components by 1 and this component by 2. This is a local order of components in case when they are different. And using this, we can define the sign. The sign of the differential. So the sign is a multiplication of 3 signs. So the signs of 3 types of permutation. So permutation appears when we change the order of the component from one state to the other state and use this local origin at the cross. Maybe I show how it can be done on the example. Let us consider this simple diagram of Hopf-Link. So we can choose this local sourcing orientation. It generates 3 or 4 dots because on each edge the orientation are disagreed. Then we consider the smoothings, the Kaufman states. On each state, on each component, we choose a point, these stop points, and also we number the component. First component, second, first, and then we also choose direction at these crossings, and this direction gives us a local numbering of the component. Local number of the component. Or let us look at the complex. We have this diagram. So when we pass from this state to this, we should apply multiplication, co-multiplication from one component to two component, multiplication, co-multiplication, and apply the involution style. Let us look at this map. Why we have these two tiles? Because we must do the following. We start with this state, and then we have mark at these distinguished points, but we apply smoothing at this crossing 1. So we should move this mark to the place where we change the smoothing. And on this way, we meet only one dot. That means we should apply this involution 1 for first component and the second component. That's why we have these two tau. And after a smooth, we get a mark here at the crossing C, and we should move it to this star. And on this way, we don't meet any dots, so we apply nothing after the multiplication. And as for the sign, you see that the local numbering coincides with the global numbering, so the sign is +1. So we have this map. I look, for example, at this map. This map why we have the sign -1? And because when we apply smoothing at this second crossings group, and here the local origin disagree with the global one, and that's why we should add the sign minus. And the other two maps can be constructed analogously. So, in this way, we get a complex. You can check that this square is anti-commutative square. So it gives the homology Z4. Homology of the Hopf link. And the theorem is what we get in the following way is complex. This complex, in fact, coincides with the complex defined by Vasily Manturov and Dyer Kestner Kaufman. And if you this coincides with for the choice when you take the canonical sourcing structure defined by the orientation of the diagram. And if you choose another sourcing structure that corresponds to the parity cycle generated by virtual crossings, you get the unoriented Havanov homology defined by Baldrige, Kaufman, and this construction leads to these two complexes. And the final remark is you can apply this construction not only to the ordinary Havanov homology, but for any Frobenius algebra with involution, you just need some this property. And if you take the universal Frobenius algebra, then you can take this involution. So you can check that this properties will be true, and thus you can define the corresponding complex. And as a special case of this universal Frobenius algebra, you can get Havanov homology if you take parameters equal to 0, h2, and h1 equals to 0 and t equals to 1. You get Lie homology. Lie homology was also defined by Manturov and the Kastner. And if you take h equal to 1 and t equal to 0, you get the Banatan homology of virtual links. So you can homology, and in fact, Lie homology and Banatan homology are trivial. That means that they are equal to ground ring power 2 power the number of components of the link. And that's because you have some contraction. In this case, this Frobenius algebra diagonalizes, and you can take, for example, the Turner article where he proved that in this case, where the Frobenius algebra is diagonal, we have trivial, in this sense, homology. Real homology in this sense. So that's all. Thank you for your attention.
Well, thank you very much, Igor. That's really interesting. I think we've got time just for a couple perhaps of questions. Are there any questions?
Well, I have written something on the chat line.
Sure. Yeah, okay. Well, perhaps Igor can answer that. I just wondered if this source sink construction is due to a biquadral with two elements. Is this true? I recall.
What's your question?
Well, this source sink construction, or the is I think is a coloring by a biquadral with two elements, black and white.
Oh yeah.
A global sourcing structure.
Yeah. But anyway, that was anyway very interesting, and we've rather overstayed our time a bit. So I shall.
I'm sorry.
That's okay. But it was very interesting talk. I'll stop.
Indeed. Before you stop, Igor, please send me your slides.
Okay.
I will put them in our Dropbox.
And I just have to say that next Friday we have an additional talk because the speaker couldn't talk on a Tuesday, and so it's the same time but on a Friday, and it's by.
Oh, that's this Friday.
This Friday, it's Giles Garden who's got an example of a knot with of a group with the integer ring has a unit, a non-trivial unit, I think. But anyway, I'll send around details. And then in a week's time, Tuesday, I guess, I don't know what, maybe Lou will give a talk, or maybe there'll be someone else, but I'll send around details.
Okay, I could. Sure.
Yeah.
In fact, I'll give a talk about the work we did with Heather Dye and Aaron Kastner about the Nikonov homology. We'll follow directly along with Igor's talk.
Oh, good. Okay,
yeah.
That sounds good. Okay, well, thanks again, Igor. Very interesting talk, and I'm going to end everything now. So, bye, everyone.
Bye.
Thank you.